In this podcast, we'll go over strong electrolytes and weak electrolytes and non-electrolytes, and we'll throw in some equivalents just for good measure. We'll start off with some definitions. So if we consider something to be an electrolyte, it's a substance that conducts electric currents in water. A non-electrolyte is a substance that does not conduct electric currents in water. Nice and simple and easy to start. Now that we know that electrolytes conduct electricity in water and non-electrolytes don't, let's get into classification of substances based on those definitions. So you can have strong electrolytes and you can have weak electrolytes. And they're very similar to how we talk about strong acids and weak acids. So a strong electrolyte, just like a strong acid, is going to completely dissociate or separate into ions when dissolved in water. So thinking back to our acids and bases unit, so strong acids and bases are going to completely dissociate in water, as well as soluble salts or soluble ionic compounds. So the example that you're seeing here is sodium chloride. It's added to water. Water is not shown here. It is going to separate because it's soluble. It will separate into sodium cations and chloride anions. So it's separating into those, and we talked about the solvation shell that would form as well. Looking at our image, strong electrolytes, we see complete dissociation. So the pluses are completely separated from the minuses. You have water surrounding all of those. Other examples of strong acids and bases would be sodium hydroxide, hydrochloric acid, any of those strong acids and bases. A weak electrolyte, just like a weak acid or base, is going to slightly dissociate in water. Mostly, though, you're going to wind up with these uncharged particles. So looking at the weak acid ammonia, it will accept a proton from water, so it forms the ammonium ion and the hydroxide ion. However, really, most of it stays unchanged. Think of this as an equilibrium where it's favoring the reactant side. So mostly you have the uncharged ammonia ion. It's not an ion, ammonia compound. So here's an example of that where we have some dissociations. We see that those are dissociated, but mostly you have these neutral compounds. So it's showing that the plus and the minus, those two that would have dissociated, are still stuck together. It's still a neutral compound. And finally, we have non-electrolytes. These do not dissociate at all. They're not going to conduct electricity. And examples of these are covalent substances. Covalent substances haven't had a transfer of electrons. They're not going to dissociate the cation from the anion because they don't have a cation and an anion. So think about things like glucose, which you're seeing. It will not separate into any ions. It will remain completely unchanged. So sugar is an example of this. That's not to say that you wouldn't get water surrounding it. It can interact with water. It's just not going to dissociate into ions. And because it doesn't dissociate into ions and there's no charge, we're not going to get an electrical current to travel through that solution. Let's drive the point home. So first things to think about for electrolytes and non-electrolytes is your compound soluble? Okay, if it's an ionic compound that has high solubility, it's going to dissociate. Great. If it has low solubility, most of it's going to remain as this precipitate, as a solid in solution. You're not going to get very much of these charged particles separating. And finally, looking at these from a visual aspect, strong electrolytes will completely dissociate. Notice that the plus and minus charges are surrounded by water. They're not interacting with each other. In a weak electrolyte, you'll have mostly uncharged particles. You'll have some separated ions, and this can conduct some electrical current, but not as strong as when you have full dissociation. And finally, a non-electrolyte, there are no charged particles in here. There is no dissolution. There's no separation. It's not going to carry an electrical current. So this is a great example of what we mean by conducting electricity in solution. So the first example, we have a separation of your anodes. We have a cathode with a positive charge and an anode with a negative charge. There's your cathode, there's your anode. And so if you have a solution where you don't have any dissociation of ions, say it's a covalent substance, or it's a water insoluble substance, because you don't have those charged ions, it's not going to conduct electricity and close that circuit from one side to the other. So non-electrolytes do not conduct electricity. Solutions that have some separation, so here we see some neutral compounds, here we see some charged particles, they're able to conduct electricity and complete the circuit between your anode and your cathode. They don't do it very well though. So what we expect to see is a somewhat dim light bulb. It's not going to be the brightest that it could be. When we use a solution that has a strong acid or a strong base or is a strong electrolyte, and we can expect complete dissociation, so every part of that is dissolved, you have separation of your ions, it is going to transfer, it's going to conduct electricity really well, and you're able to complete that circuit from your anode to your cathode, and you're going to wind up with a much brighter light. So we could see this in lab if we were to set up solutions of non, weak, and strong electrolytes and connect them to electrical current. So our last topic under electrolytes and non-electrolytes are equivalents. So an equivalent is a number of moles of charge that a mole of ions contributes to a solution. So equivalents are a relationship between moles of ions and the charge within a solution. And we represent these as equivalents per mole of an ion. So think about the absolute value of the charge of the ion for these. So for example, sodium has a +1 charge. It would transfer 1 electron to an anion. It has a +1 charge. So 1 mole of sodium with a +1 charge is equal to 1 equivalent of sodium. So we would call that 1 equivalent per mole. Calcium has a +2 charge. So 1 mole of calcium with a +2 charge is equal to 2 equivalents of calcium with a +2. So we would describe this in terms of the equivalents. It would be 2 equivalents per mole. Notice that we are not including the plus or the minus sign for that. That's where that absolute value of the charge comes in. We're just talking about what the charge contribution is to solution. Looking at an anion, the chloride ion with a -1 charge, so it's accepted an electron, has a -1 charge, so 1 mole of the chloride anion is equal to 1 equivalence of the chloride anion. So we would also describe this as being 1 equivalent per mole. And I know what you're thinking. What does this have to do with anything? I'm so glad you asked. Join me on the next slide, please. Why do you have to learn about equivalents? Let me tell you. Because electrolytes in blood plasma and IV solutions are reported in milliequivalents per liter. So that's going to be a metric unit. We can convert between milliequivalents and equivalents using our metric stair-step chart. So looking at this IV bag, which I have blown up to make it bigger so that you can see, notice that this is reporting our equivalents in milliequivalents per 100 milliliters. So I guess that one's a little bit different than what I just told you, but still metric units still works. So it's telling us that we have, for sodium ions, we have 15, and for chloride anions, we also have 15 equivalents. So what's really important here is when we put solutions into our patients, we want to make sure that the positive charges cancel out the negative charges. You don't want to have an imbalance in ions in the body. So our positive ions always have to balance out the negative ions in solution. So here we see an example. If a solution of potassium chloride has 40 milliequivalents per liter of potassium ions, it has to also contain 40 milliequivalent per liter of chloride ions. So our IV bag already told us that this was milliequivalents per milliliter. So our IV bag follows this rule that whatever you have in terms of positive ions has to equal what you have in terms of negative ions. chemistry matters.